Okay. Так. Okay, so in previous lecture we have stopped at the following observations about maximal tori and the action on the flag varieties. So let me recall what important properties we have established. So G will be algebraic group. So now we consider that the field is algebraically closed so far. And this is essential since in this case we have the Borel subgroup and the maximal torus. Yeah? So Borel, the maximal torus can be chosen in the Borel. So we consider the set of fixed points on the flag variety. So this is a standard action, and we can consider d fixed points here. So d fixed points, and of course d fixed means that the stabilizer contains this t, and evidently these are in bijection with Borel subgroups. Containing T. And on previous class we have for a general setting, so S is just a torus. So we have considered the action on the set of fixed points, and we noticed the following that about the orbits. Yes, so we noticed first fact that centralizer of torus in G acts connected component of centralizer acts transitively on a connected component of this set of G mod BIS. And notice that this was as a byproduct of the byproduct of the proof. We see that these connected components are just disjoint unions of varieties. So since it is one orbit, yeah. Mm-hmm. So this connected component is a closed set. So now that connected component is a closed set. And we see that it is a union of connected component of fixed points. Fixed points as a closed subset. And so we see that you have finite union of the orbits. So finite union of closed orbits. So that they are automatically disjoint. And so they are disjoint. Yeah, so the argument is the following, that we have considered connected component. It is a closed set. We proved that the centralizer acts transitively. Yeah? So that means it is one orbit. You have so they at least cannot intersect. So they should be disjoint. So this is about this main theorem, and then we discussed several lemmas. When the torus is maximal, yeah. So when the torus is maximal, we have said that if you have T is a maximal torus, we consider centralizer, so of G, then centralizer of this torus is contained. Yeah, and notice that we proved that centralizer is connected. Yeah, in connected group, the centralizer is connected. So, let me put 0, but the mark G is connected. Then centralizer is connected. For algebraic torus. Yeah. So this is very non-evident, I would say, because for other groups it could be really not connected. For example, for finite groups. Yeah. So so it is contained. So the centralizer is also contained in any Borel subgroup. Containing T. So of course one cannot expect this about general torus. Yes, so let me note that maximality is essential here. Yeah, so here we used that maximal toruses are conjugate in any group, and in particular in B. So we used that maximal toruses tori are conjugated in any B. Yeah.
After all, the identity is a torus.
Hmm?
After all, the identity is a torus. So.
Yeah, yeah. Of course, yeah. But I would like to have at least a non-trivial example. So to illustrate how it looks like. So let us consider something like matrix algebras. And here you can you can notice that toruses are diagonal submatrices. And toruses can be rather different with respect to this embedding, but if you do something like you can take subtorus, yeah, like this for S, just to say that these are non-zero values and non-unit values, and these are unit. Yeah. So you see that the centralizer should be something like this. Yeah. So this is this block matrix. Yeah. So of course you may just think that you can take the eigenspace of the torus and put, for example, embed the torus diagonally in the collection of eigenspaces. So to say something like this, yeah. So T2, etc. T2. So you can do it blockwise. So what will be the centralized? Yeah. So of course the reason is that if you just can calculate the action of the torus on adjoint action on the matrix, yeah, and how it will look like on arbitrary matrix. So it has values aij. So how approximately how they will be multiplied.
I remember like you said, I actually don't know why it is that, but I remember that you said that it's Ti times Aij times Tj the negative one.
Yeah, yeah. So you see that. If, for example, this values,
It's precisely like that.
yeah, it's precise like that. So you just, I mean, it is a direct calculation, or you just can do it via vectors. Yes, I mean, you may think that toruses proceed with dilatation, and this is so it multiplies basic vector, then this is a corresponding coordinate of basic vector, and then you just look at how this corresponding this becomes the coordinate corresponding to the J's i's eigenvector, and it is multiplied by Ti. But notice that so you can see what is the centralizer here. Yeah. So we can recall that you have to write down this blockwise matrix, yeah? And in these blocks, the corresponding eigenvalues will be different. So if you want to calculate centralizer, these blocks should be 0 blocks. Yeah? And so here, this acts like a diagonal matrix, so you can put everything in this block. Yeah. So you see that this restriction will be a scalar matrix. So this will be how this centralizer looks like, and definitely, so Borel subgroup here should be upper triangular. Yeah, and it is clear that so since it is a subgroup, so that preserves the space, Borel subgroup should be also upper triangular here. So this is impossible. So this is, of course, not contained in the Borel. Not contained. And your example is, of course, more convincing in the Borel. Yeah. What?
And is it right that the structure of the exact torus that we chose is like diagonal matrices times like smaller GLN, right?
Yeah.
And then we can say that GLN is not solvable, so it cannot be a subgroup.
Yeah. But yeah. So so this was important for our observation, and then you can do. So we have proved the following. So also also we shall have to recall them. About the while group that so if you have T maximum torus, then while group of T in G, so that is normalizer of T in G modulo centralizer, so acts transitively and actually simply transitively, so meaning that there is the bijective correspondence on the set of fixed points. So that's why we have the corresponding bijection, and also we proved the important thing that
Simple is the same as free.
yeah. The simply the word is simply transitively. Yeah. So freely. То есть просто транзитивный термин. No, so for myself, I do not like the words that are not self-explaining terms. So this is so freely is more. I would say freely is more just a self-explaining term. Freely. Yeah. So and we have proved the following. So if so also technical lemma about the while groups. So if you have a dimorphism between groups, so notice that just dimorphism can be quite interesting when it is in characteristic sphere. It is quite many of them. And so if you have this epimorphism and phi t is maximal torus in G, then actually here and B is Borel and U is maximal unipotent. Yeah, then the image of T is also maximal torus. And you have the map between while groups. Yeah, so you have also so for phi of B is Borel in G tilde, and phi of U as well. Phi of U is maximal and unipotent. So you have the map of fixed points. Let me put B tilde, and this is T tilde. And so this is surjective.
So the group will be G tilde.
Group is G tilde. Thank you. So this is surjective, and this map is injective. Injective. If kernel, kernel of phi is contained in any Borel subgroup of G. So this is quite important observation for us, since we have bijection with the while group. So since we have bijection between G mod T and the elements of the while group, then the same holds for while group. So, and this is actually the motivation because of considering this subset, because it is not clear a priori why we should consider the subset geometrically, but if you want to study the while group and the system of. I would say that this is motivation after abstract. So usually, maybe it is historical. What happened before introducing this algebraic counterpart. Yeah, so people considered the theory of Lie algebras, and yeah, so maybe I should finish the phrase. So the same holds for while groups. And the application, so it is important to say that application of this is just main application of this remark, of this lemma. Application is when when this radical contains it depends on the situation you want to consider. Sometimes you want to keep the torus action. So application is the following: is passing from G to G mod radical of G if you do not want to keep torus action, or from G to unipotent radical. So here, of course, radical is contained in this. So it contains it is contained in any Borel subgroup. So you can just take this for connected component of radical. So radical, and this implies that so this condition of lemma holds automatically. So let me now let me just say where we go actually. Yeah. So and what we want to obtain. So let me recall some system of roots in Lie theory. For algebras, for system of roots for Lie algebras. Recollection. Yeah, so usually one does the following. So one starts with Lie algebra, and first one. So for Lie algebra, you can always also define radical, which is a maximal solvable ideal. And you can consider, there is a criterion, Cartan, this is called Cartan criterion. That says that G is solvable if and only if its killing form is degenerate. So it's I shall recall what is killing form. Is degenerate. Meaning that, so killing form, meaning that we can consider the action of G into on itself, just via a joint representation. So so better to write it down that G maps to GLV of G. Yeah, so via Xi maps to operator Xi on something, on lose an argument. This is called a joint representation of Xi. And then
It's a little bit different, right? Because it implies that whenever the algebra is not semi-simple, it's solvable, which could not be true.
oh, is 0. Sorry, thank you very much. Is 0. Identically 0. Yeah. So this means that out of this here we can derive that if and killing form is the following, of course. So just let me Хорошо, что на одну страницу очищаю. Yeah, so killing form, there is invariant bilinear form. Defined as the following. So if you have psi of eta, you have operators in.
So again, it should be the restriction of the killing form to the first commutant should be 0.
Yeah. Нет, ну это же не про инвариантную форму. Оно же у вас же, точно, да. Is 0 the restriction, yeah. On the commutant, of course, yeah. This is actually first reduction, so restriction of killing form on commutant is 0. So so you have psi and delta, and you can take composition of these operators in GLN and take a trace. So this is, and it will be invariant with, in a sense, that psi of eta. So like you have derivation. So and zeta plus eta psi zeta is equal to 0. So like you take this bilinear form and you act on it by a joint action like derivation, and it will be 0. So you see that if G is so G is semi-simple, if and only if. This means that it doesn't have radical at all. Yeah? So radical of G is 0. So here you see that actually the Lie algebra can have center, but the center acts as a zero, by zero if you look at the joint representation. So G is semi-simple if and only if killing form is non-degenerate. Is non-degenerate. And here you notice that here you define maximal torus. So maximal torus is a maximal nilpotent algebra that coincides with its centralizer. So maximal nilpotent algebra such that T coincides with normalizer. This implies that this is commutative. Yeah, so this is precisely Cartan subalgebra, characterization of Cartan subalgebra. Notice that automatically, if your algebra is nilpotent, and then the torus inside it, so it should be normalized and centralized by it. So it is commutative subalgebra. And one can consider decomposition and it is diagonalizable. It is semi-simple. Yeah. So actually, you consider the weight space decomposition, so that. And one first consider just like Jordan normal form. Yes, so we consider not the weights, but the characteristic subspaces. Yes, so kernels of first one consider kernels of operators of this form. Yes, so for toruses. For the powers of them, yeah, and then you prove that by semi-simplicity, you prove that only you have only just that it acts diagonally, so you have only eigenvectors. Yeah, so in this case.
I think it depends on the exposition.
Yeah, so non-degeneracy. Yeah, of course, but that refer more classical by Serre. Yeah. Degeneracy. Applies that G of alpha is eigenspace. So these are eigenspaces, and you can just think of them as the roots. So your eigenvalues are linear functions. And notice that so what we have here. So first of all, alpha appear with minus alpha. This is important property. Yeah, so this is corollary of non-degeneracy. So corollary of non-degeneracy of killing form, simply you prove that the pairing g of alpha, g of beta is 0 if alpha plus beta not equal to 0. So this implies that since it is a direct sum, the restriction of, so T is orthogonal to any sum, and you have the following orthogonal decomposition. So T plus G alpha plus minus alpha. I mean, G minus alpha can be an empty, of course. So this is decomposition in two orthogonal spaces. And this implies, since if you have decomposition on orthogonal non-intersecting spaces, so then the restriction of killing form, so since this was non-degenerate on G, this implies that restriction of G of T, so restriction on any of any, so if you have V is direct sum of orthogonal spaces, so bilinear form is non-degenerate if and only if restriction of, so Vi is orthogonal to Vj, so restriction to Vi of this if and only if restriction to any Vi is non-degenerate. So this means that this this is irrelevant. So restriction of killing form is non-degenerate, and restriction of killing form on these sums, G alpha plus G minus alpha, is non-degenerate. And since the pairing of G alpha with itself is 0, so then you should have non-trivial pairing with G minus alpha. Yeah, so since G alpha is equal to 0, then for any psi in G alpha there exists beta in G minus alpha, so such that psi is not equal to 0. And also it's important, but it's not trivial. This is some calculation. Notice that this is calculation with SL2 triples using representation theory. I'm recalling all this stuff just to understand what will be analog of these things in our case. So idea of calculation. Yeah. So let me say about that dimension of G alpha is equal to dimension of G minus alpha. This is of course the corollary of non-degeneracy, but so this is corollary from here, but dimension of G alpha is equal to 1. So this is proved, and notice that alpha is not proportional to any beta until alpha is minus, beta is minus alpha. So let me say positive statement, alpha, if alpha is proportional to beta, then alpha is equal to beta or alpha is minus beta. And this is done as follows. So this is done by searching of SL2 triple. So meaning that you're searching but for the elements of alpha and G minus alpha and the H alpha inside torus. So such that this is SL2 and this subgroup generated by it is isomorphic to SL2. And then one uses representations as a theory of SL2 in order to understand this dimension. So this is derived from representation theory of SL2. Yeah, so actually one proves that the group, otherwise the group generated by these elements will be not semi-simple. So, I mean, if there are some additional elements, then one derived that some group will be not symmetric. So this what it really tells you about all this stuff. That first of all, that SL2 triples are important. They're derived like this, and then after that, when you already have SL2 triple, and one notices that E alpha, F alpha are nilpotent elements on at least so E alpha and F alpha are unipotent, are nilpotent. And as the joint operators, and this because they shift eigenspaces by alpha and F alpha via SL2 theory. So you can form something like exponent of E alpha T exponent F alpha and the exponent E alpha T, something like that. So maybe a minus should be somewhere, so I mean inside the exponent. But one introduces this element, and it is what? It is, first of all, it is element of the group, yeah? So because exponent is just so it is it is in automorphism of G, yeah. So it is the element of corresponding. So if Lie algebra came from the group, then this will be a group element, and it has the property that it as alpha normalized maximal torus. So as alpha normalize maximal torus, and acts by the reflection, and this is most important one for us. This is a reflection on H. So on T. So it acts like the reflection, meaning that what it does, it normalizes maximal torus, so it preserves the decomposition, so preserves decomposition of T into G alpha, but of course it can interchange factors. Yeah, so but interchange factors like if for by evident reason S alpha of G beta is equal to the G of S alpha beta. Yeah? And what is more important here that if one opens if you take beta, so just maybe xi, but to say xi because I do not say that it is a root xi that belongs to T. So if xi is orthogonal to alpha, then S alpha of xi is equal to xi. And S alpha of alpha is equal to minus alpha, and it is a direct check in SL2 triple. Yeah? So this is a direct calculation. In matrices, yeah, so in SL2, subgroup of SL2, because this elements, of course, sits in SL2 subgroup. So you do this direct calculation, and you see that this set is very important. I mean, this is just the set of. So notice that here I have. Actually, alpha is functional on the set of toruses, but I have identified, so note that we identify T and T dual because the roots are functionals actually on T, on the elements of T. And so here I have written this thing that xi is orthogonal to alpha, of course, meaning that, so I should have written that xi of alpha is alpha of xi is equal to 0. But anyway, so this shows that yeah, so the condition is alpha of xi is equal to 0 is the codimension 1 condition, one subtorus.
Keep in mind, do we consider S alpha as the element of the automorphisms of the algebra G?
Yes, yes,
okay.
yes. I mean, this exponent gives you
The element in GLG.
yeah, it is a formal exponent of T alpha can be viewed as just an element of automorphism of the algebra. Yeah. So, and this is of course. I mean, you shouldn't consider some larger subgroup. I mean, you shouldn't have the property that Lie algebra comes from Lie group here.
Yeah.
So far, we do not have to use it. However, a posteriori, such all semi-simple algebra comes from groups, at least, or from some group. It can be simply connected or not simply connected. These are details, but I mean, always you have a simply connected group corresponding to this algebra. So, but what is important for our program that we should realize in purely algebraic setting, first, so this kind of condition. So this is codimension 1 subtorus, and we can consider, so we can calculate here the centralizer of it. Let us look what is centralizer of this subtorus in G. Yeah. So so notice. Yeah. Of course, one should look at the eigenspaces. It is subtorus of T. So it of course preserves the eigenspaces. So we have very simple situation that you have to just to consider its action on the eigenspaces and to understand which we should include in the centralizer and which we shouldn't include. So this is consistent with the composition. So for me, sometimes I prefer delta for the roots, and it is run. I would maybe in the paper I would prefer delta, but I can use it randomly sometimes. So notice that of course evidently centralizer contains T, and also if yeah, you shouldn't take picture. I mean, we shall have lecture notes. I mean, yeah, of course you can, but I mean, there is no need at least to do it. Yeah.
Sometimes lecture notes are delayed.
Yeah. So you may do it, but I just wanted to say that. Yeah. So. Yeah. So anyway, it will be saved. I hope, but still, I mean, I do not say that you cannot take pictures. So. Then, yeah, so I would say we shall do our best to save it at least. Yeah, so if, so of course T is contained here because S is subtorus in T. So, and note that, so if beta is not orthogonal. So beta, I mean, let us look about G alpha. So since this torus is orthogonal, any element of this torus is orthogonal, so to alpha, so since alpha is equal to 0, S acts trivially on G alpha and G minus alpha. Yeah? And this, of course, and of course, for other elements, yeah. So for any, so since it is the system of linear functional, and this is codimension one subspace for any beta that belongs to the root system, there will be some element of psi in torus, so such that beta of psi is not equal to 0, and this implies that G beta is not in the centralizer. The centralizer of S in G. Yeah? Just because that on beta we have the action. Yeah, so on element F. Just on element. So on the element E inside G beta, so this psi of head of psi of E beta is just E beta itself with the coefficient beta of psi. So definitely, so this is not in the centralizer, and since it is the sum consistent with respect to torus, we just have to include the corresponding eigenspaces in the centralizer. And what are they? So this is precisely the torus and the remaining SL2 triple. So this group, so the centralizer of G is of S in G is just T plus G alpha plus G minus alpha. So notice, so of course in T there would be central element, so H alpha, E alpha is F alpha, so SL2 triple is contained in this group, and the quotient of this by the center, or of its center, so let me put it some group H, so даже не знаю, какой буквы обозначить. Ну, давайте вот так. Yeah, so if you have A modulo center of A is just SL2. Isomorphic to this SL2. Because the remaining, you will have H alpha and complementary torus S. And so the torus S is in the center. Yeah? So centralizer of A is of course the torus S. So after taking this quotient, you will have this SL2 triple. So you see that we can try to recover algebraic groups and these reflections via this SL2 triplets. So we are searching for these toruses. Yeah? So by these toruses, we can recover SL2 triples simply by the following. So you take the torus, so just the other way to after we know the theory, so other way to recover SL2 triple is the following. So take S to be the set. So this is hyperplane in the torus alpha of set of elements of psi in the torus such that alpha of psi is equal to 0, and the centralizer of S modulo S is SL2 triple. And yeah, so if so here of course you have one-dimensional torus. So reflection is what? Reflection is the set and the element and the normalizer. So you can also characterize S alpha. It is an element of automorphism of SL2 triple. So automorphism of SL2 triple. I mean it maps to so it is automorphism of G. So and also you have, so it has characterizing property that S alpha acts, so S alpha acts on T mod S, yes, so acts on, so it fixes S, fix S pointwise and it acts on the quotient, and quotient is what? Что?
Should be one dimensional.
One dimensional, yeah. So it is just our algebra, well, C over the complex numbers of the field. Yeah? So base field. And it is just K, and so it is automorphism. Actually, a priori it could act by the roots of unity, but it should, I mean, on one-dimensional space. But it actually acts on by -1. Yeah? So here it acts by -1, and later we shall understand this that it is conceptual. I mean, from this will just. I mean, of course, if we look at this moment from the viewpoint of Lie algebras, you cannot say by which scale it does it act. Yeah? So it should act by automorphism. It is yeah. So actually, we can derive it by knowing that s square is equal to 1.
Yeah.
Yeah? But it's not needed. If we shall get this automatically if you will look from the viewpoint of algebraic. So this one, yeah. So this, yeah. So we can understand that yes, that scale is -1, since s alpha square is equal to 1, but this this won't be actually needed. It will be automatic. So yeah.
We know that there is beta there is such that there is psi that is not the kernel of beta. It's like the last line of the right word.
Yeah, yeah.
Because
Just
it's
it is
proportional
called,
to
yeah. So it is just hyperplane. I mean, alpha is the only orthogonal vectors to all vectors of
So
hyperplane.
we know this because beta is not proportional to alpha.
Yeah, yeah, yeah. No. For beta, yeah, I should write it, not proportional to alpha. So we know this more or less automatically since it is defined. So all vectors of S are defined by one condition: alpha is equal to 0, and this is hyperplane. So yes, it's good time to make a break. Yes, so it is perfect time to make 5-minute breaks. And after that, what is the reason of this recalling of this exposition? We should forget about Lie algebras because sometimes it is hard to produce the correspondence, especially in characteristic P, and or moreover in characteristic P. It can happen that Lie algebras are not semi-simple. Yeah? So their representations are not semi-simple, and it is hard to make this theory work. But we shall see that these basic observations that I made, so that some of them are group-like. So like you can, instead of algebras, you can introduce the corresponding groups, and then we can derive this as some automorphism. And also there will be flag varieties that will be related, will be very helpful in this situation.
And theory will hold even in positive characteristics.
Yeah, yeah. And you will see that it's not actually, that the killing form is degenerate is important if we work with Lie algebras, but actually this can be you can understand that it is a reflection from the first of all you should have a space where you should act. So this is of course not Lie algebra. Yeah? So, and the second is that but it will be the space of the same dimension, and actually this will be a lattice, and the algebra, and we can produce a vector space via the integer lattice. And moreover, so this so let me just, it will be not very fun.
Это лучше следующий лекцию.
Да, конечно. Ну, то есть иначе смысла не было напоминать. Да. Не, ну как бы я думаю, что не стоит нам как бы вспоминать детали о алгебре, хотя это несложно.
Это вот придет, потому что это, к сожалению, придет, потому что я алгебре, то есть вот это я еще понимаю, но дальше не.
Ну хорошо, но мы просто это реализуем как бы вот в тех, в других терминах. И в этом весь фокус. Это вот как бы отсюда примерно класс Zhgun. Что такое класс Zhgun? Это как бы можно это другие векторы, то есть других сечений Просто вот это отображение, о котором вы говорите, постоянно, его, как бы оно, просто обычно, вот, как бы для чего нам нужна обильность, рождаемость глобального сечения. Чтобы что-то можно было сказать о сечении, о общих свойствах.
Да,
Например, там мы знаем, что обильность, она влечет дополнение до нулей, это афинное многообразие. И еще вы знаете теорему связности, что у вас множество нулей, оно всегда связано, приводимо. Да, для общего оно вообще гладко, да? Обычно, для произвольного оно связано. Это как бы можно использовать. То есть у вас там есть всякие теоремы о непустоте и...
Я занимаюсь, когда из того, буквально необходимости для обеспечения в случае, когда наследник меняет. Там он даже доказалось. Но дальше интересно, что делать, если это не линейная система, а однокорректная система. Ну, потому что положение становится.
Что, какая?
Если это не, если это не линейная система, а линейная система, то есть когда там, не линейное настроение, а векторное настроение. Нет положения нужно. И вот там ровно то, что нужно, это хорошо.
Но и там проблема в том, что вот это вот как бы геометрическое свойство обильности.
Обильность нужна. Вот это суть дела. Мы вообще не в том ощущении, что нужна не обильность, это просто глобальная врожденность.
Да, глобальная порожденность, конечно, слабее.
Да.
Но это чаще всего такие вот тонкие геометрические свойства. В смысле, надо смотреть на ваши теории.
Да.
То есть я говорю, совсем производительный случай. У вас должно быть.
Нет, там есть такие условия, для того, что линейная система есть отражение ПМ, там нужно написать условия на то, насколько линейная система разделяет точки. Если недостаточно разделяет эти точки, то общее сечение сдает необходимую форму величины.
То есть как бы вы меняете вообще обильность действительно в какой мере это разделение точек общего положения.
Если оно очень сильное разделение,
Оно, да, плюс касательно.
обильность имеет такое свойство, что если обильность не нести 20 точек, то она дает
Просто, наверное, почему люди, почему люди любят обильность, видимо, легче проверять, чем условия разделения.
Да, но условия разделения формируются размерность, поэтому очень проще. Нужно отображаться как в случае не всем, нужно отображаться в P. В случае конкретной системы конкретно как меня, но как будто бы этого мало. То есть достаточно там. Ладно, конечно, с ним не стоим, можем после.
Ладно, да, интересно. Yeah, so, okay, so let us try to realize our problem now. So now we have to consider, instead of while group, so in order to study while group, we want to study fixed point sets, and we want to consider regular subtorises. So, let us call S torus S regular. the set of fixed points is finite. So notice that yeah, so actually so now we shall see the characterization of regular toruses. So actually it's this set we will see, yeah, so this S, it will contain, it will be contained in some maximal torus, yeah. So for example, you can take centralized and any torus is centralized. But a posteriori, we shall see that actually we cannot. So this is a smaller torus, so evidently this is a subset of S is a subset of G mod B T, and it is
That's first, right?
yeah, yeah. So but I would say that this S is obtained, so it is defined in T by many conditions, by many equations. And there are so much of them that it cannot really increase the number of fixed points. Yeah. So the final goal is the following proposition. So this is information about the torus T. So S is a subtorus. And the following is equivalent to that S is regular. The second is that centralizer of torus and G is solvable. So sorry. And so in this case, to that S, so centralizer of torus is contained in any Borel subgroup. So containing in any Borel subgroup containing, I mean, of course, it cannot be contained in any Borel subgroup, but in any Borel subgroup containing S. And for any maximal torus T that contains S, we have the set of fixed points are the same. Yeah, so this means that from the viewpoint of, so the question is what can, how large can S be? So such a regular torus. So let me say remark that S can be very small. Yeah. Just S in T can be even one dimensional.
In the proposition 1 and 2 is the conditions that we assume, and then
No, if and only if. I mean the following is the equivalent, and in the case following is equivalent. And in the latter case, you can do have this. So, I think that, also, so also this is, I think we shall even prove that this is a characterizing property. Yeah. So, I think we can put like this, so that all of this is equivalent. So this is 3, can be viewed as 3, and this can be viewed as 4. So this is an equivalent state. So, but let me do it more thoroughly. So this and of course, so this is for any maximal torus, and one can state for prime, so for one maximal torus, yeah. So for some maximal torus. So the set of fixed points of torus are the same. I mean, of course, I mean, as the criterion, this is weaker. But notice that this can be a rather, so if T acts, this is the condition of how we can be even one-dimensional. Because the centralizer can be rather small, the condition is that, so if you decompose T into, so T acts on V, on the vector space V, so V are the decomposition in the eigenspaces. You can just take S, the action, with different characters. So S acts with this is one parameter subgroup, so can be viewed as a one parameter subgroup. Lambda of T such that
growth groups are characterized by flags, and there are only finitely many flags that this T stabilizes.
I'm not by flags. I would say that the condition of so S can be taken to be lambda of T such that chi of I of T is not equal to chi of J of T. Chi of I of lambda is not lambda of T, is not equal to chi of J of T, and chi i's are different hypersurfaces, So the just T is not covered by the finite number of hypersurfaces. So just since T is not covered by finite number of codimension 1 varieties chi of T, so well, on the element of G, let's see, is equal to chi J of T for G inside T. So
And that's how we prove their
yeah,
invariance here.
this is how we prove actually. No, not the proposition. I'm saying that if you have, so this can be viewed on linear representation. That the torus can, the action of torus can be rather small. And actually, so thinking of this, also you can view this. So G mod B can be viewed as embedded into this subspace. So the projectilization of B. And notice that here we can consider fixed points. So fixed points of torus are just proportional vectors. Right? So fixed points of torus on P of V are just eigenvectors. Yeah, so just P of V, so such that P of V is just chi of T of V, and these are just the union of. So this is intersection of G of B, the union of I with P with corresponding eigenvectors. Yeah. So so you see, for example, that if you have this condition, that it's not the proof of the theorem because I have formulated it in a little bit different way, but it is some kind of explanation that if your torus, subtorus is sufficiently general, it we have proved that you have the same behavior on the centralizer, but then you always can look at the set of fixed points, and it is just an intersection with eigenspaces, and the composition and the eigenspaces is the same. So it is just, and this will be technically derived from what we have proved. So maybe I should destroy the enumeration. Yeah? In order to, sorry, this will be just, it is like saying for astronauts it was a giant leap for small step for the man and giant leap for the mankind. So this for the convenience of the reader, so the person who will compile lectures will have some additional troubles. So yeah, so like notice that so here you have the full length. You have centralizer of torus of G, and actually the orbit of yeah. So notice that we have the action of centralizer of torus. Transitive action zeros on each connected component. Of the set. Gmod B yes, and you can of course the if so we have transitive action, so this is one orbit, so you have the so, and in particular, you can think that it's an orbit of point B. Yeah? So, y corresponds to B. So, you see that stabilizer of the action of ZG S on EB is just intersection with B, of course. Yeah, so it's just so it is centralizer of S and B. And the dimension of the orbit, dimension of y, is just the so y is just the subset of ZGS modular ZBS. So dimension of y is just dimension of GS minus dimension of DS. So just if S is regular, so by our definition, then dimension of y is 0. Yeah, and if and only and this implies that ZGS is equal to ZBS, yeah? And this of course implies that so this implies that ZGS is solvable. And it happens if and only if, yeah? Because this is precisely centralizer in the Borel subgroup. So, this really means this means that solvable and connected. Yeah. Connected. So this implies that ZGS is contained in B. So where B contains S. So because condition that B contains S is the stabilizer, meaning that that B belongs to the fixed point set. Yeah, so the let is equivalent. Condition is equivalent that B belongs to the set G mod B. Yes. So this yeah, so this yeah, so if you have yeah, if so also you have you see that if the torus is regular, yeah, so that this centralizer, I mean, it cannot act on different points with different dimensions, yeah. So if it is solvable, then I mean, since we have proved that this happens, that yeah, if and only if it is solvable, then it also says that G, так, это будет 13, да? So if S, if S
Okay.
Mhm.
The centralizer lies in B because it coincides.
yeah, I mean, you have S is regular, yeah, so then you have dimension. Then this means the centralizer of this fixed point is just the centralizer of S inside B, and centralizer of S in. So this means that the first group is solvable because let is a subgroup of a solvable group, and also this means that it is in the centralizer, and also this means that so this also means that so if B contains S, so B tilde contains S, then you have just a second. So maybe it requires
So where's the problem?
Не, просто вопрос, что я хотел сказать. Я хотел сказать, что в частности, ну, если у нас, so I wanted to derive the following. So if yeah, so the thing is that просто тут вопрос, что я хотел сказать. Но я хотел сказать, что если мы знаем, что централизатор разрешим, то он также оставляет неподвижным все остальные точки, неподвижные точки же по БС. Потому что, ну, как бы мы вот эту вот часть, то есть смотрите, мы тут как бы на самом деле тут можно ослабить наши условия. Ослабляем мы условия так. Мы требуем не чтобы размерность всех компонентов была нульмерна, а хотя бы одной компоненты. То есть давайте это еще тут тоже ослабим. И отсюда выведем so here I want to make some additional one prime remarks, so that one component of G mod BS has dimension 0. So this is, of course, some kind of special property. Yeah? So, out of this, so notice that, so this is one of these components. So this is one of these components, and we have derived out of this that G of S is solvable. Yeah. So by the sequence of arguments, and if it is solvable, so notice that what can be said about other orbits of the fixed point set. Yes, so other orbits. So on other orbits. So other components of the set of fixed points of G mod BS. The torus, the centralizer, acts transitively. And not so other components that are projective varieties, that are complete varieties. Yeah? So centralizer also acts transitively. This implies that it should be a point because it is solved. So since the G of S is solvable, so then it coincides with Borel, yeah? So it coincides with its Borel. Then Z of G of S acts trivially on any component of GB of S. Yeah, because if your group is solvable, then any this any complete homogeneous variety is a point. Is a point. Поэтому, ну, как бы вот даже регулярность это более такое, получается условие, которое, ну, для то, что вы увидели, что там одна орбита, сразу говорят о том, что все. No, but this means that this implies that the ZG of S is contained in any Borel subgroup containing S. And also we have to make a remark about the torus itself, or about maximal torus. Yeah? Condition of the fixed points of maximal torus. So if T is maximal, maximal and contains S. So this implies that in particular T is contained in the centralizer, and we have proved that the centralizer acts trivial. And we proved that the G of S acts trivially on the set of fixed points on G mod B S, and this implies, of course, this implies that fixed points of G mod BS are also fixed points for T. And of course, if so, the last one we should derive. We can so in order to so we have derived formula the following thing. Yeah, so we have derived out of this. Yeah, so out of 1 we have derived. Yeah, so 1 implies 1 prime. Yeah. So then we have derived. I want to write down the scheme of proof. Yeah. So we have derived from 1, 3, from this 4, and out of 4, yeah. So this of course implies trivially this one, and 4 prime implies 1, and even 1, not 1 prime. Yeah. So and it implies very easily because so if T is maximal, T contains S, and if G of B T is equal to G of BS, so for maximal torus, this was finite set of points. So this implies 1. То есть мы даже лучше, чем у Хамфри это сделали. Ну, в смысле, что мы ослабили вот эти свойства. Ну, просто он так как бы не слишком тут напрягался, и поэтому, ну, как бы сложно сказать, как он напрягался, но, по крайней мере, тут он 12. Было 14. Тут, ну, как бы мы даже лучше сделали эквивалентные условия. So this means that this toruses are quite important regular toruses. Means that the torus somehow in a general position with respect to weights of the action. And now let us move to this theory of roots. And now we shall use toruses that are not regular. Yeah, so let us recall that I want to introduce. So now we shall have T maximal torus inside G. So of course we shall use the property of decomposition of the Lie algebra, but we shall have some kind of we shall study not the sub-algebras but the subgroups, and the subgroups will be studied via studying the action on the Lie algebra on the root system. So you have the root system corresponding to the maximal torus, and we want to, a posteriori, we want to derive, to understand how radical looks like, yeah? And we want to prove, so aim is to prove that radical, unipotent radical of T is equal to the intersection of all U's with the condition that U contain the corresponding Borel subgroup, so which is normalizer of so you can recover, of course, Borel subgroup as a normalizer of maximal unipotent. Yeah, so note that if U is radical, unipotent radical of B, B can be recovered. B is recovered as a normalizer of U into G. Yeah? So this and yeah, maybe it's an exercise actually. So I haven't proved it explicitly, but let me put it as an exercise. So then you can recover U by so you can intersect the U such that normalizer of G of U contains T. So you can consider those Borel subgroups are containing your given maximal torus, and sorry, it's so here it's stupid thing. So radical of G. So you can recover unipotent radical by this way, but it is not so aimed to prove this. So we shall put, so far we shall put I of T to be this group, and yeah, and we have the corresponding decomposition of the Lie algebra. Yeah? So you have this corresponding decomposition. You can take this subgroup. Of course, it contains T, so just sorry, it's normalized by T. So I of T. Yeah. So actually, yeah. So notation is yeah, so as for notation, I of T is just intersection of this, of the Borel subgroups containing T. So Borel subgroups containing T. And radical of U is the unipotent radical of U of T. So I claim that there will be, of course, torus in this group. So the claim is that the radical of unipotent radical of this one is, of course, radical of G. Unipotent radical of G. Yeah, just because the toruses I cannot say the same about the radicals, because this group contains clearly the torus itself, which can be not in the radical object. So that's why I'm a little bit messy here, yeah? Because so here I want to study this group, and if you want to write the root decomposition, it is convenient to write also root decomposition for I of t. So it is it contains t, so you have consistent root decomposition. So I of t. It's a Lie algebra. So I'm denoting it by Gothic letters. Plus here you have remaining roots that we will call psi. So psi is a subset in phi in the full set of roots. And I claim now that so since so A must understand, so since I of t contains unipotent radical and the torus, so this so moral is so that this psi is the set of roots of unipotent part of G mod unipotent radical of G. Yeah, so actually, even for without. So this is so the set of roots of semi-simple algebra. Of semi-simple algebra. So it should behave like a system of roots that we expect. And now the idea that we shall study it via the action on the flag varieties. So consider the subtorus T alpha. So this will be elementary subtorus. So it is a subtorus, so those elements of T, so such that alpha of T is equal to 1. Yeah, so it's a character, so the value of the character is equal to 1. So this is codimension 1 subset. So dimension of T alpha is just dimension of T minus 1. So so let us see that so claim that S is singular so now it's convenient to understand the toruses and to understand. So the aim is to understand regular toruses. So we have to formulate the condition for not being regular. So we have introduced this elementary singular toruses, and so from the viewpoint of just elements in the Lie algebra, so you have a system of roots. So, for example, this is a standard A2 system, yeah? And what means regular for toruses? Yeah, so for here you have a system of hyperplanes. So, and you see that this is precisely alpha equal to 0. Yeah, so this will be if this is beta, beta will be equal to 0. Yeah, so you have this subsystem of roots, and this is collection of hyperplanes. And for the V algebra, we define regular element of torus as the element outside of this set. Yeah, so xi is regular if it doesn't contain in the set of these hyperplanes. And the same situation here with the groups. Yeah, so S is singular if and only if it contains S is contained in T alpha for some alpha. So this is precisely analog.
Singular means non-regular, yeah?
Huh?
Singular means non-regular, yeah?
Yeah, non-regular. Yeah. So this is just a condition of non-general position. Yeah. So so if so proof. So if S is non-regular, so this implies that centralizer is not solvable as before. So is not solvable. And so input notice that so you have definite, but note that I of t is solvable. Yeah, just because as an intersection of solvable subgroups, it is intersection of solvable subgroups. B contains T. And this and the intersection of I of t with centralizer, it is also solvable. Yeah? But this implies that, yeah, so since this is not solvable, in particular, so the G of S is not contained in I of t, and it contains maximal torus containing S. Yeah. So if you put S to, yeah. So just yeah. So here take T containing S. Of course, take any T containing S. First, we have started with torus, but we can take maximal torus that contains this given one. So notice that S lives in torus, and this, of course, lives in the centralizer because it is commutative. Yeah. So since.
But haven't we fixed the torus when we defined?
No, just take non-regular torus. Take any torus contains this one, just any one. I mean, I do not fix it. Yeah. So you start with arbitrary torus. So take T maximal torus. Containing S. I mean, of course, as a singular if for some alpha, meaning that
For some
S is contained, yes, so this means that for some t, but so let us start with S containing t, S contained in t.
and
I mean that, so start with S contained in t. Then T alpha is subtorus of T, yes, so that we have, but if you started with, so you can have characterization of non-regular torus that as it will be contained in T for some alpha and some T, yeah? So some specific T. So T is commutative. So then this implies that T is in this centralizer. So this means that you have this decomposition, root decomposition is consistent with the centralizer and I of T. It will be also a root decomposition. Сейчас 18, да? So just this G I of T plus you will have this decomposition of G alpha of psi, but root this was a part of root decomposition, of full root decomposition of where you put centralizer of T plus where alpha belongs to phi. Yeah, so let me put G beta. And you may you see that you see the following, that this condition that Z of GS is not contained in C, so we are studying Lie algebra for the centralizer, and since we have correspondence of Lie algebra of centralizers of toruses and the toruses itself, you have corresponding decomposition in CT, and you have the system that this G beta, that beta is in phi, and you have condition that beta is in the centralizer. Yes, so beta sits in the centralizer. So meaning that so what we have obtained that there exists beta, so such that G beta is a subset of the centralizer, and it doesn't contain the FT. So G beta is not contained in I of T. Just because I of T is not F. I of T is not the centralizer. So this implies that G beta then S centralizers. So beta of S is equal to 1 on any S inside S, and this implies the claim. Yeah? So S sits in T alpha, where alpha corresponds to phi, to psi. So this is important that so that it's not just root in the root system. It is in the root system of a solvable group of the of semi-simple group of the group that will be semi-simple. So I mean, it's almost as a lemma, it's almost tautology, but it will be important for us. So now I want to discuss. Yeah, so what can be said about this So let us introduce the group G alpha. G alpha, which is centralizer of torus S, modular. So this group has evident center. Yeah, so the torus itself. Yeah. So we can consider this subgroup. But notice, just suppose S. Yeah. Let me put S where S is T alpha. Yeah. For this given T alpha. Yeah? So notice that. So of course centralizer it contains T as before. Yeah. So T contains T alpha, and this is commutative. And you see that we can look at what is semi-simple rank of it. Yeah, so the rank of semi-simple. This will be so. Of course, this group won't contain a center anymore because you can. Otherwise, you can use it to construct a centralizer of T alpha, and notice that. The center here is maximal possible because it is codimension 1. Yeah. So center. So dimension of T alpha is equal to dimension of T minus 1. And notice that we have homomorphism. So image of T is maximal torus here. Yeah. So image of T, which is isomorphic to what? T modulo T alpha is maximal torus in G alpha. So it is one-dimensional. So it's maximal one-dimensional subtorus. And this means that semi-simple rank of G alpha is equal to 1. However, it's not clear what is this group. But this group will be so this group will be well, at least it's a finite covering of PGL. So aim to prove that G alpha is a finite covering of PGL2. And if you want to speak about PGL2, you have to find the action where the G alpha acts. So to recover PGL2, we have to construct action. Of G alpha on P1. Yeah? And P1 is a flat variety. So so it will be a set of fixed so it will be a flat variety. Yeah? So now let us realize this problem. Yeah? So let us realize, so we shall understand what are characterizations of what are characterizations of EGL2 in terms of, we shall understand what does it mean that the group has semi-simple rank 1. And in order to understand this, we shall act on flag varieties. Okay, so now let me do some pre-discussion action of one parameter subgroups. Subgroups on projective space. On P of V. Because our flag variety lives actually in projective space. So, of course, we have to take the decomposition into the characters. And now, if you look on one parameter subgroups, characters are just integer numbers, yes, so weights. Yes, so this characters is just z because it is one parameter subgroup acts via parameter t, so it's just lambda t of v is just t to the power m of v for m integer, because the action is algebraic. So this chi, so we can enumerate chi's as the integer numbers. So m1. So let us enumerate them. Yeah, maybe. So m will be a multiplicity. So let me put characters. And dimensions of ki's are just this vector space. Let us put it to be n i's. So what can be said about projective space? So here you have, so if you have suppose you have a vector v. So to the vector you, it has some decomposition in the characters. And in order to understand the action of one parameter subgroup, so let us take only those chi in this sequence that are with non-zero, where Vx has non-zero. So we can assume that well, by passing to the subspace of V, to subspace of V, that all V chi are not equal to 0. Yeah? Just and now we can look at the action. So here lambda t of v acts by t in the power mi via chi. And you may see what is, you have two obvious limit points. So we have, in a affine space, you have, of course, do not have any limit points. But here, you have two limits in projective space, since we work in projective space. So you can take limit with t equal to 0. And in order, of course, if all mi's are positive, yes, so the limit will be 0. But the limit should be in the projective space, so it is just a limit of you can take the division, yeah, by any number. So it is equal to the limit t tends to 0 of this sum, yeah, divided by the smallest number.
So it would be like V1.
Yeah,
Okay.
yeah. So like V, yes. I have denoted. Yeah, so I have denoted with VKI, but of course it is better to denote it by V1. Yeah,
So
so
it should be VKI.
yeah. Yeah, so this is a, so you can divide by any number, and you can take the smallest number here, yeah, in order to divide. So it will look like, let me take limit like V1 plus the remaining sum of vectors. So via I, where T will be Mi minus M1. Denoted, and here I will be, of course, bigger than 1 here. So this tends to 0 because Mi minus M1 is positive, and so this is equal to V. Yeah? So this limit is equal to V1, and similarly for limit. So similarly. In similar way, you can take limit in a different direction in when t tends to infinity, and this will be the last vector, of course, here, yeah, because it is inverse, just Vn. So with the largest, so the with largest m. It will, the limit vector will be the vector with largest coordinate in the physical. So what is the corollary of this observation? Так, сейчас это, значит, 18 это 20, да? А это 21. 22. So corollary is the following. Is that if you have one parameter, so one parameter subgroup acts on acts linearly on X variety on close. Let me say, so acts on P of V linearly. So linearly mean lambda of T acts on V linearly. Yeah? So meaning that lambda of T is a subgroup on GLV. Yeah? So
basically, there is no other way to act on a projective space. Is it?
Как бы вопрос, как вложено ваше проективное пространство. Не, но автоморфизмы но я вот хочу именно вот так, как я сказал, чтобы они...
Вот понималось в этом утверждении?
Да, ну просто... Ну да, что оно поднимается до линейного действия. Ну в том смысле, так бы она действовала по проективным преобразованиям, да? Она действует линейно. Вот, но so I shall give you some counter example. Yeah. Also, then you see that so you see the following. So and lambda t acts on some closed variety x, closed invariance variety. Then lambda t has at least 2 points, two fixed points, and if dimension of x is larger than 1, then it has 3 fixed points, at least 3 fixed points. And this means that, and of course, if it is one-dimensional, it is just a closure, so it is just P1. Yeah, so of course, just X is isomorphic to P1 in dimension 1 case. Just for this, and just because it's a closure of one parameter subgroup. I mean, it is 2-point compactification of A2.
I mean, there is a toric action on the nodal curve, right?
Это как раз, yeah, so, оно как раз, вот, я именно про него я хотел сказать, что это как бы контрпример. Но лямбда тогда не, смотрите, тогда вот это P от V, оно...
Нет, ну там прям торм вкладывается, что там так, ну не надо, скажем, простые недальные, а испедальный кубик.
Но испедальная кубика не вкладывается как под многообразие в P от V в качестве линейного действия. Нодальная кубика не является замкнутой орбитой однопараметрической группы в P от V при линейном действии. Вот что это значит.
Если будет действовать...
Да, если вы действуете на векторном пространстве, у вас всегда будут две, вот таким образом, как я сказал, у вас будут всегда две неподвижные.
То есть я могу подействовать на...
Вы не можете, да, подействовать на объемлющем пространстве так, чтобы это была орбита.
Не орбита, надо будет вариант, не орбита прям.
Ну, да, ну, в смысле, инвариантно под многообразие. Но это в том числе доказывает. Вот вы сами, да, я только хотел сказать про этот пример, что, как бы, конечно, у вас бывает компактификация GM, которая... So there, of course, compactification of GM as the nodal curve. So this is nodal curve, but nodal curve doesn't embed in projective space in the set. So, okay, so maybe it's a good point to stop here. So I want to briefly explain this corollary, which is more or less evident. So Here this means the following. So you take x and you just want to do the following. So you just
Если я возьму Тор, подожди, период спрашиваю. Не, период спрашиваю.
Yeah, so so of course proof one that you have lambda t, and so since the closure of lambda t is inside PV is just it is isomorphic to P1, so we have found infinity point and 0 point, and actually so you should. I mean, it's more or less evident that it is P1, but you can formally check it by these coordinates. Yeah, so by looking at homogeneous coordinates and actually by projection to this subspace of the fixed points. And this, in order, а у вас пара следующая, да? У вас пара сейчас будет, да?
Ну, будет.
А через сколько?
Сейчас скажу. По идее.
Ну, минут 5 у меня есть еще?
Наверное, да.
Ага, хорошо.
Ну, я пару веду, поэтому...
Не, ну, как бы, нет, это, конечно, хорошо все, но, как бы, есть этика, поэтому... Yeah, so this is isomorphic to P1, so this implies that this embedding, you have embedding of P1 inside X. Now, if you have, if you have, so let us take basis, so V1, V, N is a homogeneous, a basis of eigenspaces, so basis of eigenvectors, and so V1 is fixed point with minimal value. Ну ладно, давайте тогда лучше закончу.
Чтобы успели сохранить это.
А, да, чтобы успеть сохранить. Вот. Ну, просто в следующий раз я там расскажу.
Есть вопрос, да.
Да.
Что там закончили?
А?
Мы закончили?
Да, давайте сохраним сначала.
Или вас я возьму к испытанию кубику, полезть в ней. А вы умеете сохранить?
А?
Вы умеете сохранить, да, то есть не
Ага. Сейчас.
Наверное, должен.
Наверное, да. Вот. Сейчас. А где?
Окей. Значит, это должен.
А, ну да. Сейчас. Сегодня какая дата? А, ну 29-е, 29-е. Все было. Да. Спасибо. Че, китайский? Оп. Так. Что это?
Честно кажется, нужно
Может, вот это? А,
Да.
вот. Спасибо. 29/09. Ну и подчеркну 2 доска. И тут. Да, сделайте импорт.
Импорт. В смысле?
В PDF.
А.
Ну что, тогда выходим, да? А выйти? А, вот.
Вопрос, я возьму...
Да, сейчас, давайте еще запись.
Да?
Ну, она была, да, только...
Вы будете записи там с какой-то задержкой?
Да я думаю, что я